Hello everyone. So now, as we are seeing for the lecture of basic signals and system, that is, so till now we have completed the first unit, and now we are moving on to the second unit. So in first unit we have seen what are different type of signals and what are the different operations we can perform those signals, what are different type of systems and what are the properties, basic properties of the system, how we can identify the what by seeing a function, how we can identify that what type of system is this, or also we have seen that if suppose we are having some basic signals like we have unit step signal or we have ramp signal or we have a combination of some signals. So, how we can represent a signal into a combination of those basic signals. So, now moving to the second unit, here we will see Fourier series. So, in unit 1 also we have seen that there are means we have studied about the periodic signal. So, what is the periodic signal? Periodic signals are basically those signals which repeat themselves after a specific duration of time, and that specific duration is called as the time period of that signal. Okay. So, now in Fourier series we will see what we will see there was that a signal can be represented in the form of the summation of sine and cosine. So, means any periodic signal with some condition, that condition is called a Dirichlet condition. If that satisfies those condition of Dirichlet, it can be represented in the form of summation of different harmonics of sine or cosine. So, we will see. So, what is the definition of? So, here we can see a Fourier series of a so, basically a Fourier series of a periodic function is a representation that resolve f 2 into dc component and the ac component. That means, if there is any function, it will have two part, ac plus dc. So, basically ac of any signal is basically the average value and dc is the AC plus DC. So, basically DC is the average value. So, any signal or any function we can represent in the summation of DC plus AC. This AC will consist of different sinusoidal functions or different frequency of sinusoidal signals or cosine signal. So, basically, so how we define it? That is summation of DC component, AC component comprising an infinite series of harmonic sinusoidal. What do you mean by harmonic sinusoidal? See, suppose if sine omega t is fundamental value of sine omega t, then sine 2 omega t, sine 3 omega t or sine n omega t, all these value will be called as what? The harmonics of the sinusoidal signal. Okay. Now, next, so see how, suppose what you can see this, there was a one basic signal, it is like a, suppose it is a unit step signal. So, so what we have seen unit step signal, what is unit step signal? Unit step signal is a signal which is having 0 value, before t is equal to 0. Like suppose if I have to represent this signal in a form of mathematical form, how you can write f t is equal to 0 for t 0 for t less than 0 and 1 for t greater than 0. So, see, so this is basically a unit step signal. Now, we want to represent that unit step signal in the form of a Fourier series expansion. So, what we have done, see, we have used different sinusoidal signals, and we can represent these sinusoidal signals, this unit step signal into a form of summation of different sinusoidal signals. So, this is the basically an example of how we can expand or how we can represent a signal in a function into its summation of different harmonic of sinusoidal. Again, we want to the next example, see again here. So, what is this? Here we have a square wave, and what we have done, we have represented this square wave into a form of using summation of sinusoidal and cosine signal. Similarly, we have triangular wave, then we have sawtooth wave. So, what we are doing here, we are representing a signal or a function into the summation of different sinusoidal or cosine signals. Okay. So, now these are the basic example. Now, next, so see, so what is the condition? What is the condition? Foremost condition, we can represent only those functions which are periodic. That periodic function can only be represented or can be represented in the Fourier expansion. So, this is the basically the formula. What I have told you is the function should be what? Is DC plus AC, DC plus AC. So, this is basically the DC value and this is basically an AC value. This is basically this much is the AC value. Okay. So, this infinite sum is known as Fourier series. So, what is the condition we have to remember? Period should be t, it must be a periodic function. Okay. Now, next, so what I have told you initially itself that any signal, if you want to represent it in form of Fourier series, then that signal, that function must satisfy 2 to 3 conditions. So, what are these conditions we will discuss here. So, it is saying what is those conditions are called as Dirichlet condition. So, what is Dirichlet conditions? See, the first is function must be well defined at every x interval. That means function must be continuous. Function must be continuous. Whatever function we are trying to represent, it must have a property of continuity. Again, second is f must be continuous or have finite number of discontinuities. Suppose if a signal, if a function is having discontinuity, for example, suppose I am having this type of function, So, basically this function is having a time period of t. So, for if we want to analyze for one time period, we can see we basically have two discontinuities. So, what does this condition say? F must be continuous or have finite number of discontinuities. That means this signal is having, this function is having two discontinuities, means that is finite discontinuities. But if we have a function something like this, suppose so this is the basically time period of this function. So, what we can see, this signal or this function is having so many discontinuities. It is having, means not finite discontinuity, it is having many discontinuities. So, it violate the one of the condition of Dirichlet condition. That means this function, instead of being, even if it is a periodic function, still we cannot represent it in the form of Fourier series. Third is f dash must be continuous or piecewise continuous within the interval. What does it mean? See, basically the third condition what we want to say, suppose a signal. So, basically this signal means ki it should have, the function must have means countable maxima or minima. The function must have countable maxima or minima. For example, suppose I have drawn one triangular signal. So, if we see this triangular signal is having one maxima and one minima. Okay, one maxima and one minima. Now, so basically it should have one maxima, it should have countable, like for discontinuity we have a condition, it should be finite. Similarly, we must have finite number of maxima or minima. Whereas, suppose I draw a signal like this, if I draw a signal like this, so you can see there are lots of maxima and lots of minima. If we draw a signal like this, we will have lots. Let me draw in a broader scale. See, suppose if a function is like this, again from here it is going. So, if this is the one time period, so here you can see there is I have drawn it border way where there are many maxima, many minima. So, this also violates the condition of what? Dirichlet condition. Thus, function must have finite number of maxima or minima. So, these three conditions must be satisfied for any function to be represented in a form of Fourier series. Okay. Next, also see any two vector, this is basically any two vector which is A or B satisfy following condition mutually orthogonal. So, what do you mean orthogonal signal? Suppose if there are two signal, if the product of those signal is 0, then that signal is called as basically mutually orthogonal. Basically that is called as mutually orthogonal. So, this I have already informed that for Fourier series signal must be periodic. What do you mean by periodic? Periodic means the function value must be same after a certain duration of time. After a duration of time, it must be repeating. For example, suppose this is a signal, so it is repeating after what? After t duration. After t duration, this signal is being repeated. So, basically the function, so this function is having a time period of t, which is called as fundamental time period. Okay, it is called as fundamental time period. So this is t will be called as fundamental time period. Okay. Now next, see, so how we can represent, so now we have seen the condition for which is required for representing as any function into its Fourier series form. So now how we represent and what are the different quantities or what are different points which you remember. See, a function which is satisfying Dirichlet condition, can be represented in a trigonometric. Basically there are two forms of Fourier series, one is trigonometric form and other is exponential form. Okay. So basically here we are seeing the first we are seeing trigonometric form. So trigonometric form, what I have told, there is two quantity, one is average value and this is the basically representation of DC signal. So what are these? So these are different coefficient, Fourier coefficient, and this is basically the harmonic frequency. So suppose here if you change the value n is equal to 1, then it will be fundamental value. Again if you make n is equal to 2, then it will be second harmonic, then n is equal to 3, it will be third harmonic. So this is the basically representation how we will represent any function which is satisfying Dirichlet condition into a Fourier series form. So this you have to remember, this form. So I will also tell you the value of a b, a n and b n. What are these values? These are basically called as Fourier coefficient. So see, first also before that let us see what are the few integral value of sinusoidal. See, the advantage of sinusoidal signal is, as we have seen that in electrical also, that there are many advantages of sinusoidal signal. What are the main advantage? See, you know, in electrical system basically we use, if you think in a mathematical manner, then you can say, because in signals basically in electrical we use mostly sinusoidal signals. So basically the differentiation and integration of sinusoidal signal is also of the same nature. Same nature means what? It is sinusoidal itself. Means like, see, sinusoidal, cosine, both waveform are of same nature. You cannot say both are different, but both the shapes are same. So this is only the sinusoidal signal is the one whose differentiation and integration also give you the same type of signal, same nature of signal. Okay. So see, you must be remembering this, what, see, as integration of a sinusoidal function for a one time period is always what? 0. Why 0? Because as we know, a sinusoidal signal is basically symmetric around the, is basically an odd function. Sinusoidal function basically odd function. What do you mean odd function? Odd function which is symmetric around origin. The function which is symmetric around origin is basically odd function. So if you calculate for one area, so we can see it is having positive area, similar negative area. So if you sum the area of positive area, negative area, then for a time period it will come equal to 0. So we have to remember, similar is the case for cosine signal. In a time period of t, the value of it will have equal positive plus negative area. So this is the integration you must remember before learning that coefficient value of a and b n. Again this is one more. So this is what I have told you, what, this is a condition, integration of sine into cos dt is equal to 0. So this only I was telling you about the orthogonal signal. This is basically a property of orthogonality. What? Two functions, two signals, if product is coming 0, it is a orthogonals, both are called as orthogonal. Similarly, if you are keeping n, if you are changing the frequency, then again it will is equal to 0, where m is must not be equal to n. Again this is the value, if both cosine also, both sine also, it value is 0. So this is the what is basically what? Orthogonal property. Next, see, this also you must remember, what is this? The integration of sine square n omega naught t d is equal to t by 2. This you have to remember. Why you have to remember? Because see you can easily get this thing if you remember the value formula for cos 2 theta. What is cos 2 theta? 1 minus 2 sine square theta. So if we are from here, if you find out the value of sine square theta, we will get sine square theta is equal to 1 minus cos 2 theta by 2. So, replace here integration 0 to t sin square theta is equal to 1 minus cos 2 theta by 2 d theta. So, as we know the integration of cos theta will be what is equal to 0. So, what we will get from here 1 upon 2 t. So, here also t by 2. Same is the result. So, this result also you must remember. Similar is the case for cos square, because here we know cos 2 theta is equal to 1 minus 2 sin square theta t. Also we can write cos 2 theta is equal to 2 cos square theta minus 1. So, using this relation we can easily derive this, or we can write it as. So, basically this is, so what we have studied, there were 3 coefficient a v, a n and b n. So, why are you writing a v? A v means what? This subscript represent average value, average value. Okay. So, a v is basically the average value, that is why we are calling it DC value. What do you mean DC value? Means average value of any function. Again next we are having a n. So, a n is basically 2 by t 0 to t integral t f t cos n omega naught t. See, also one you must remember one thing. See, in some formula, in some books it might be represented like this: a naught f t cos n omega naught t plus a n So, in some book it might, they might write 2 here, they might write 2 here. So, there it will not require to write 2 here. So, you have to remember any one form, you have to check for this 2. Some few people write 2 here in the a n value, somewhere it is written this 2 is included in the this formula itself. So, we have to check for this. Okay. Now, see, so this is again similar for b. For b n, what is the formula for b n? 2 by t t 0 f t sin n omega naught t. See, here also one must remember one thing: sin omega naught t and cos omega naught t. So, we have to remember this is basically sin omega naught t is basically what? A even function, a even signal, and cos omega naught t is basically an odd signal. Okay. So, why I am saying this? Because sometime it will be easy for us if we are required to find the value of b n. Sometime if we are required to find the value of b n, so what we will be required to do? See, if there is sine which is a even signal, or cosine which is odd signal, and here if we get any function which is odd, if we get any function f t which is odd and sinusoidal which is even, so we know odd, any odd function or any odd signal into even signal will give us what? A odd signal, and we know that odd signal is symmetric about what? Origin. Odd signal is what? Symmetric about origin. So, we can directly from this result itself, from here itself we can write that value of b n is equal to what? 0. Value of what? b n is equal to 0. So, here you have to check if we are able to find the nature of this signal or the nature of this function, whether it is even or odd, if we are easily able to find out what is the nature of this function. So, by seeing without calculating we can say the value of b n or value of a n, directly we can say. Okay. Okay. So, now as we have seen the value, now so there are basically, so these are some effect of symmetry on Fourier coefficient. So, see, now we are required to find out a naught, a n and b n, these 3 value to represent any signal or any function into its Fourier series. So, we are having some tools, or we are having some shortcuts, or we are having some observation that if we are able to find those observability in that function, we can easily determine the value of these signals. Okay. So, what is those properties? What is basically symmetricity. So, see, the basically there in this function you will find basically 4 different type of symmetricity. So, we already know even and odd symmetry, because in signal we have seen odd and even symmetry. What is even symmetry? Any signal or any function which is symmetric around y axis, any function or any signal which is symmetric around y axis, that is called as even symmetric. Again, any signal or function which is having symmetric around origin, just now we have seen, any signal or any function which is having symmetricity around origin, then that is called odd signal. Here we will see two extra symmetricity, that is half wave and quarter wave. What is half wave symmetricity and what is quarter wave symmetricity? Okay. So, see, so this is already seen, we have seen. So, again you can see this is even function. How you can say this even function? See, all the three signal is symmetric around origin, means if you fold this, suppose if this is if you use this axis as a mirror, then you will get this mirror image. Again if you will use this as a axis, you will get this mirror image. So, these three are example of what? An even function, because it is symmetric around y axis. Again, so see, suppose now here what I was telling you, suppose if you are having any, why you are getting Bn is equal to 0, if any function which is even will give you Bn is equal to 0. Why? Because as you know Bn contain cos term, function which will be having Ft even you will have sine term or similar term. So, it will give already what? Odd terms, and we know any odd signal, any odd function will have what? Bn is equal to 0. Similarly, what is odd function? Any signal which is symmetric about origin. See, origin, if you use this mirror as origin as mirror, then you will get this mirror image. So, what will happen this? See, when function was even, we were getting Bn is equal to 0. When function is odd, we will get An is equal to 0. So, these are the basically two shortcuts we must remember. So, see, if we are having Bn, one more thing also, if we are having odd function, so what is odd function? Odd function will have AB and An both is equal to 0, because odd function, the average of odd function will be 0, and because it is having odd, and there will be odd function, and An contains sine term which is also an odd. Okay. So, this will also give you a what? A 0 value. So, AB and An for an odd signal will be 0, and An for even signal only Bn will be 0. Okay. Next. So, next we are coming to half wave symmetry. What is half wave symmetry? See, this is the condition for half wave symmetry, this is the condition for basically half wave symmetry. See what? If we, so Ft is equal to Ft minus T by 2, means if there is a function, suppose if you can easily remember, suppose there is some, just remember a shortcut to see whether signal is half wave symmetry, because if you check by using this, then it will take long time. Just remember one thing, suppose you are having one signal or any function, do what thing? Use this as a mirror, fold it to the left, then fold it to the up, means one left folding and one upward folding. If by doing this you are getting the same signal, if you are getting the same signal, then that is the shortcut for telling that it is having half wave symmetry. What? Divide a signal in by 2 half, you have to do what? Left folding, then upward folding. If you are getting same signal, then it is called as half wave symmetry. See, again see what? Fold it to the left, then fold it to the upward, you will get again this value. See, fold it to the left, fold it to the up, you will get again same shape. So, that is what basically half wave symmetry. What is quarter wave symmetry? Quarter wave symmetry is having one additional thing, it is half wave symmetry plus it is also symmetric in their respective half. See, this signal is also symmetric. If we draw axis here, it is also symmetric. It is, if we draw the axis here. So, basically these two are the see, now see, it is also half wave symmetric. So, see, because if you fold it left folding and then up folding, you will get same signal. So, quarter wave symmetric is half wave symmetric plus individual half symmetric. See, it is also symmetric around this. So, you can see this signal, this is also symmetric around this. If you fold it like this, it will be also symmetric. So, this is basically example of quarter wave symmetric. Okay. See, now also we can combinedly we can represent this signal in a form of this. How we can write? See, we know cos A plus B, here there only is. See, basically we know cos A plus B is equal to cos A into cos B minus sin A into sin B. So, we can represent this into this form. We can represent that our function f t in this form as well. Okay. So, how we can write this? See, we will divide and multiply with value and we will get this form. And how we will find value of phi n? The value of phi n will be tan inverse A by B. See here, tan inverse B by tan inverse B by A. So, this is one relation. This is one relation. If we represent that Fourier Fourier series in cosineal form, only if you want to represent the function into cosine form. See, if you only want to represent this function in cosine form, only cosinal, then what you have to do? You will represent like this. A will remain as same. Only there will be new coefficient, that is a n, and this will be the final value. Okay. So, there is also another form. Initially I have told you there are two forms. See, one is a cosinal form or trigonometrical form, and another is exponential form. So, in next lecture we will see how we can represent a signal in a exponential form of the Fourier series. Okay, thank you.